Hi folks, I thought that today I will just make a presentation on how to work out the top of descent point. Now, before I continue, there are many videos on this platform whereby many authors have explained the top of descent calculations. We call it energy management for various fleets and also rules of thumb, which are great. And I do encourage you to see those, as many as you can, so that you get a better understanding on how to work out the top of descent profile rather for your descent and energy management issues. Now, when we fly the Q400, I've been observing something which I've always been interested to understand, how the Q400 calculates its top of descent point. And I came up with an explanation which I'd like to share, and also I'd like to get more comments from those of you who fly the Q400, the veterans of you, and any other ones of you who maybe understand this thing better, and share and see if we can discuss as regards to how the top of descent is calculated. So I have a diagram here whereby we are at a height h and we want to descend to the height small h. So for example, we are at 25,000, we want to descend at, let's say, 2,000 or at sea level or the like. Okay, so the question is, how do we calculate top of descent? Now, what I've done here is that this is the normal 3-degree glide slope for top of descent, which has been explained, as I said, in many presentations, many videos on the YouTube, in books. They use 3 degrees, and that all of us know or should know as aviators, that we normally use a 3-degree reference to work out our top of descent point. So this descent rate corresponds to 3 degrees. Now, if we reduce the rate of descent, that's where the study which I was doing came about. If I reduce rate of descent, what I'm going to see is that the angle, or what we have to observe, or what we notice, is that the angle of descent decreases. Because if we reduce the rate of descent, we will start our descent earlier compared to when we were at, let's say, 3 degrees. Now, what I have observed on the Dash 8, because I fly this aircraft, so I'm referring it to that one, but I'm pretty sure it should be same or similar on other fleets, is that if the rate of descent is 1,500 feet per minute, it gives us a 3-degree slope. Now, if we, let's say, go down to 1,200 feet per minute, typically use, let's say, we're descending to sea level airports. Why we do this for sea level airports? To avoid pressure bumps and have a comfortable transition from where we are to where we are heading, because the pressure where we are higher up is way less than the pressure at sea level. So we incorporate that change gradually, so it doesn't hurt the ears and cause discomfort to the occupants of the aircraft. Okay, so we all know this formula. By the way, the title of this presentation is to calculate top of descent by incorporating change in distance due to change in rate of descent. I call it delta D, this part here. So if my aircraft was here, when I program the rate of descent to be 1,500 feet per minute, it will be there with a distance from where I'm descending to as, let's call it D1. Now when I reduce rate of descent, let's say 1200 feet per minute, I observe that the distance now from where I want to descend to where I am has increased to d2. Okay, so how do we incorporate that change of distance in our top of descent calculation? Okay, let's say we want to start descending earlier, all right, or later. For example, how do we incorporate change of distance? Yeah, so this is not from any book. I am the one who has figured this out, but I would like confirmation, of course, from all of you aviators to see if it makes sense. It would be much appreciated. Okay, but yeah, so basically top of descent, as we all know from all the presentations from the YouTube platform, from books, is change in height multiplied by 3 plus any speed reduction distance that we need, plus or minus the wind. If it's a headwind, we start our descent later. If it's a tailwind, we start our descent earlier. This is how far we know. But now let's say we want to start our descent by a shallower rate of descent, okay, for some reason. All right, so we can also incorporate how much we'll add to our originally calculated top of descent point using the 3-degree concept. So until here we've calculated, but that was based on 1500 feet per minute for this particular presentation in this aircraft. So now we decided, okay, we're going to go to 1200 feet per minute. So how much further will I have to move my top of descent point? That's where I want to get to. So in so doing, I will first of all use a bit of mathematics, but we don't do this in the flight deck because we don't have time to pull out calculators, as you know, and do trigonometry and all that. We don't have that time. So I'm going to go through all this, what I've done, and I'm going to come up with a general rule. If it's acceptable, I would appreciate it. If there's any changes or anything that can be done, also appreciate it through your comments. Simple right angle triangle concept, where we use something called SOHCAHTOA, for those of us who remember our high school mathematics. Tan of an angle is equal to opposite of the adjacent. So in our diagram here, tan of 3 is equal to opposite, which is delta h, the height to lose, h minus h, okay, divided by adjacent d1, and tan of delta 2 is again height to lose divided by adjacent d2. Now this formula here is very important, which is found in certain aviation books, if not all of them, I think we do, which says that the rate of descent is equal to the theta times the ground speed times 100 over 60. I will not go into the derivation of this one, okay, in this presentation, but there are fabulous presentations on the platform where some authors have actually derived this formula, okay, or actually have used it to find the link between rate of descent, the angle, the ground speed, okay, and I encourage you to see those presentations. So when I use this formula and I use the two rate of descents that we typically use in our operations, for rate of descent of 1500 feet per minute, the angle was around 3 degrees, 3 degrees. For rate of descent of 1200 feet per minute, the angle was 2.1 or 2 degrees. Okay, going into a bit of mathematics now, since we want to find this distance here, the delta d, it is d2 minus d1. I hope that's agreed. We want to find the distance that we have to increase by from what's the pre-calculated value at this rate of descent 1500 to our program rate of descent 1200. So it's d2 minus d1. When I make d2 and d1 the subject in these equations, simple maths, and then when I manipulate the formulae, I'm going to get d2 is obviously delta h over tan 2, and d1 is delta h over tan 3. These are in feet, and we should know that we want to nautical miles. We want this to be nautical miles. So we have to divide by 6080. which is the same as multiplying by 1 over 6080. This is your high school simple maths. When I use some manipulation here, okay, I factor out the delta H, and I bring it outside. It's going to multiply by the numerator here, so delta H over 6080 will be outside, multiplied by 1 over tan 2 and 1 over tan 3. Remember there was delta H here, but we've taken it outside. It's a common factor, so we have achieved this. Now this is roughly 9.6. Okay, if you do this in the calculator, 1 over tan 2 minus 1 over tan 3 in a scientific calculator like this one, all right, you will get around 9.6 or something. All right, 9.6. All right, so that's roughly equal to 10. Okay, as we know that as pilots we don't use exact figures, but we use approximate figures that bring us to the near exact value, because we don't have time to pull out calculators in the flight deck and start doing calculations mentally. We can't do that. Mental calculations means that have to be done by mental methods, not by machines. So this is 10, and if I do 10 over 6080, all right, so if I just do that here for now to show you, if I do 10 divided by 6080, I get 1 over 608. Okay, so which means that this is 10 times delta H over 6080 simplified is delta H over 608. So still 608 can be approximated to 600. Yeah, so which means that now delta D is roughly equal to delta H over 600. Still some big numbers to use here, but what we can do, we can reduce this down further. So delta H, let's say we were at 22,000 feet and we descend 9,000 feet. Yeah, 22,000 to 9,000. What's the difference? 13,000. So we can just ignore the last two zeros, okay, and we just do the 100 number that results divided by 6. Okay, so this delta H here, we don't need to use the full number in the thousands, just knock off the two zeros at the end and divide by 6. So you should know a 6 times table. When you do that, you will be getting approximate distances, okay, as in how much further you should move depending on the situation of that day. So this formula here is not found in any textbook, or I haven't seen it. If there is, then please correct me, but I haven't seen it. But I have just put myself into this task of understanding why the distance changes when the rate of descent changes. That's the whole concept of this presentation, why the distance changes and by how much the distance should change. So this is what I've done as a particular study, which I'd like you to even give your input. In the subsequent presentation here, you will see some videos where I took videos from a recent flight where I was changing the rate of descent and I was observing where the top of descent was moving. For those of us who fly the Q4 and any other magenta representation of an FMS aircraft, the top of descent, you will see it moving back and forth when I change the rate of descent from 15 to 1200 and so on and so forth. And I will take you through also what I've done there, and let's hope that this does make sense and it's usable, and it will be much appreciated, as I keep saying, for your inputs. Okay, so let's go and now see the presentation, the videos rather, which I've taken live in the aircraft while I am changing the top of descent, the rate of descent point. One is for a descent from 22,000 to 9,000. The other is a top of a descent from 23,000 to 2,000 feet. Okay, so just to keep those figures in mind, and then let's have a look and see what is happening to the top of descent point as we change the rate of descent. Thank you, and as always, Be safe, and much appreciated that you are benefiting from these presentations of mine. Thank you.